let me give a little introduction. So Oriol got his PhD in 2008 in the Universitat Autónoma de Barcelona with Professor Ana Sampere. And then he got a Humboldt Fellowship to work with Ignacio Cirac at the Max Planck Institute for Quantum Optics in Garching. And then while he was there, he proposed and theoretically analyzed how to use optically levitated nanoparticles for cavity optomechanics and how to, in that way, prepare large quantum superpositions. And that's something that we're going to hear about today from him. And then moving on in 2013, he moved to Innsbruck to start his own research group with a joint tenure track position as a full professor at the University of Innsbruck and also junior director at the Optics and Quantum Information of the Austrian Academy of Sciences. He got tenure in 2018 and he's been awarded, among other prizes and fellowships, an ERC starting grant in 2013 and an ERC synergy grant in 2020 that he's coordinating. So I'm really looking forward to hearing your talk, Oriol. Over to you.
Hey, thank you very much, Gavin, for the introduction, and to all of you for the invitation. It's really a great pleasure to have the opportunity to speak in this setting with so many experts and so many of you interested in pushing the limits of quantum mechanics and macroscopic scales. So the topic of today's talk is actually on precisely this topic, so towards macroscopic quantum physics with levitated particles. And I will start with a bit of an introduction from a broad picture, and then I will narrow to the topic of the talk. So actually, one could say that in the context of levitated particles, this is a story that started back in the 70s with the work of Arthur Ashkin, who invented optical tweezers to trap polarizable particles with light. And he even did experiments of trapping particles in vacuum already back then. But as we all know, the main focus of optical tweezers was to basically trap particles in liquid for biological sciences and biophysics. Of course, the work of optical tweezers also triggered all the development in atomic and molecular AMO, basically physics, to use also lasers to trap and control single atoms. So of course, the impact has been enormous from optical tweezers. In 2010, inspired in a sense by this work of optical tweezers, some of us proposed to actually optically levitate one of these electric nanoparticles in vacuum and inside an optical cavity, so that one could cool down, in principle, the center of mass motion to the quantum regime, and then consider the quantum physics of these nanoparticles. And in a sense, that was also very much in the context of cavity optomechanics at that time. And already by then, we realized that the important differences of a levitated particle compared to cavity optomechanics is that, of course, we don't have a mechanical support. And this basically means that the object can be freely translated, can be rotated, and can even be dropped. Okay, and these are very different features to what one can do with cavity optomechanics. So today, there are many experiments around the world, also many in the UK, where experimentalists trap nanoparticles in high vacuum. This is actually a picture that I like a lot from the group of Lucas Novotny, ETH Zurich, where you can see an optically trapped nanoparticle. We see the scattered light of the particle, and that's why it looks a bit bigger than what it is, and you can see it on a camera. And this is just trapped with an optical tweezers. And somehow now this field is kind of growing a lot. There are many experimental groups interested in that. And in this field of, if you want, levitodynamics, in this sense, what people want to do is study the physics of levitated objects in vacuum. And that's now very general, okay? And the first thing that was interesting to do with these particles was to try to remove the thermal energy they have in the center of mass motion. So that's what we call typically cooling. One should not confuse center of mass cooling with bulk cooling. So we are not talking here about bulk cooling, but just center of mass. So we remove the thermal energy from the center of mass motion. And in these optical traps or other traps, this is basically a 3D harmonic a 3D harmonic potential, and the typical trapping frequencies of these harmonic potentials are of the order of 2 pi, of the order of 10 to the 5 hertz, so 100 kilohertz. And if you remember from the basic quantum physics of an harmonic oscillator, if you have a particle and you remove all the thermal energy, you would hit the ground state of this harmonic potential. And the wave function of this ground state would have a length scale given by the so-called 0-point motion. And this is given by the square root of h bar divided 2 times the mass and the frequency. And for the typical particles that we are dealing with, of, for instance, 100 nanometers, this mass is of 10 to the 10 atomic mass units, so it contains billions of atoms. And that means that the 0-point motion has a very minute scale of the order of 10 to the minus 12 meters, so smaller than the size of an atom. And actually, it's very beautiful to think that you have this hot particle and experimentalists can remove all the energy so that it basically only vibrates to this tiny length scale of 10 to the minus 12 meters. At the same time, it also shows why this is actually challenging, okay? And if we think about the kinetic energy this particle has at the ground state, this corresponds to a thermal energy of 10 to the minus 6 kelvins, more or less, so microkelvins, okay? So that was the goal, to try to cool down this particle to the quantum regime so that we can prepare the center of mass in a quantum pure state, okay? From the quantum physics point of view, that's a way of preparing a pure state of the center of mass. And it was only very recently that this has been achieved experimentally. So in particular, last year, there was the experiment in the group of Marcus Aspelmayer, where using cavity cooling, they could cool down the motion to the ground state. And also, a few months after, there was also experiments in which, instead of using a cavity to cool, what we call passive cooling, what experimentalists did was to basically measure the position with a lot of precision of a particle that is in free space, and then use this information about the position to feedback this information by applying some force into the particle, in that case electrostatic force, such that the kinetic energy is also removed. And in that way, they could also cool down to the quantum regime. And so these are two different types of experiments, passive cooling and active cooling. And the active cooling experiments were done also by the team of Marcus Aspelmayer and also by the team of Lucas Novotny. So at the same time, while these experiments focus on optical levitation of the electric particles, today there are many other types of experiments one can do where particles are manipulated not only optically, but also electrically and even magnetically. For instance, with Paul traps or with magnetic traps. And this automatically means that there are many types of particles you can consider, not only the electric nanoparticles, like in optical levitation, but also other types of materials, such as magnets, metals, diamonds with quantum emitters, even superconducting particles, graphene, and even these nice experiments with superfluid helium droplets. And this is important to realize that actually, if you use laser light of a particle that absorbs, then since it's in high vacuum, it heats up and you can photo damage the particle and actually burn it. So for levitating particles that can absorb laser light, you need to use other type of manipulation with other fields that are not optical. At the same time, there are other shapes that have been considered, such as spheres, but also rods, dumbbells, platylets, and in particular in the context of these different shapes, dumbbells, for instance, people have been studying also rotational degrees of freedom of these objects. And actually there are these incredible experiments where they rotate these dumbbells to gigahertz frequencies, which means that a particle spins 10 to the 9 times in a second, so 1 billion times per second, which is hard to visualize. So that means that basically now people are interested in levitating any type of object in the microscale and study its dynamics, external, internal, rotational, and so on. And why people are interested in that is because of the following applications, which one can perhaps organize in four big areas. The first one, which is moreover the core topic of this colloquium series, is of course to push the boundaries of quantum physics. Given the fact that the particle now can be cooled to the ground state, one could consider the possibility of preparing now macroscopic quantum states, delocalizing the center of mass over large scales. In this way, kind of studying the potential transition between classical and quantum physics, and even the possibility to being these objects so massive to start to look at the interplay between quantum physics and gravity. In that context, I like to think always that in a sense, we are following a top-down approach where we take a massive object, we make it small, and sufficiently small such that it can start to behave quantum according to quantum physics. Whereas the traditional quantum optics approach was more a bottom-up, where you manipulate an atom, maybe you put another one, you start to generate complex systems, many-body systems, and so on. Here we do the opposite. We just take a piece of material which is very complex and we make it sufficiently small such that we can remove all the thermal energy and it can behave according to quantum physics. The second area of applications is in the context of highly sensitive detectors. These objects are massive and they are very fragile once you remove all the thermal energy, and therefore can be used as sensors. And clearly there are two applications, one for fundamental physics, where, for instance, to give you an example, one can exploit the fact that these particles have a high mass density, not only a large mass, because in terms of mass, the mass of a particle is comparable to the mass of a gas of atoms, but the high mass density plays an important role because it allows us to, for instance, treat the center of mass really isolated from all the other degrees of freedom, and also it allows us to place this mass close to another one at very short distances, such that we could measure potential corrections of Newtonian force at short scales. And I'm not an expert, but my colleagues from high energy physics always tell me that this is one of the most interesting possibilities to measure gravity at very short distances. At the same time, there are the potential technological applications to use these levitated particles as gravitometers, as gyroscopes, accelerometers, and so on. And many people are also pushing that direction. Perhaps a much less discussed application, but nevertheless, in my opinion, very interesting, is the possibility to also study the internal physics of these objects, to study the internal degrees of freedom. And I don't mean here the scenario where you embed quantum emitters in a particle, but actually where you look at the internal solid state quantum excitations of the object, such as acoustic phonons, plasmons, magnons, and so on. And this could be very interesting because these objects are very isolated, very far from any substrate, and therefore there could be some, and very confined and very isolated. And this leads to very interesting internal solid state physics. Furthermore, you can place these objects into very extreme conditions by generating a lot of stress by spinning them. When I said before that they spin them to gigahertz frequencies, they cannot go to higher frequencies because the stress is so high that basically they disintegrate the particles. So you go to the extreme stress, to a critical stress before the particle disintegrates. And there might be interesting physics you can explore at that extreme regime. Such as, for instance, a generation of phase transitions or so on. I think this is a line that I foresee will be explored much more in the future. And last but not least, it is also interesting the fact that these particles are trapped in 3D harmonic potentials, but these harmonic potentials can be deformed. You can prepare all type of potentials, double wells, inverted, and so on. Furthermore, one can control the interaction with the environment really well. One can remove the gas slowly, go from damped regimes to under-damped regimes. One can think about putting many particles and study how they interact also due to near-field electrodynamics, how the internal excitations tunnel and so on. So one could visualize having a lattice of these particles of maybe of different type and looking at all these interesting physics. So I think that perhaps explain why so many experimental groups are getting interested in levitating particles beyond what we will discuss today, which is, of course, one of, in my opinion, also one of the most exciting possibilities, which is to push the boundaries of quantum physics. And I just want to quickly review that actually after there were the first proposals, some of us thought about the possibility, of course, after you are able to cool down the particle to let it switch off the trap and let it evolve such that the wave function expands in free dynamics. And by that time, we thought about preparing superpositions by letting the particle pass through a cavity such that it couples to the quadratic part, so that the light couples to x square. And by a discoupling, you could perform an x square measurement and prepare some superposition and see, so that you could do like a double slit experiment. That was back almost 10 years ago. Some years after, I also want to mention that we also worked on the possibility to now exploit the fact that you can dynamically modulate the potentials. And here we were trying to push what is the biggest size and superposition one could think about preparing. And by excluding many possibilities, we ended up with the idea of magnetically levitating superconducting spheres and let them skate through a potential landscape, such that when the particle moves, it sees, for instance, harmonic potential and inverted free potential and so on, such that the double slit is done by modulating the potentials, but without doing that externally, but just passively, because by the particle moving on the reference frame of the particle, it sees a dynamical potential. And actually, in that context, we also discussed, because we were pushing so much the size of the particles and superpositions, that here we would enter in what we defined by in that paper in 2016 about the gravitational quantum regime, in the sense that there is this scale where gravitational effects and quantum effects could enter into play. And in particular, we focus in that paper a lot on showing that in that regime, one could falsify the Dioschi-Penrose collapse model in the absence of a free parameter by using an homogeneous mass density, which is the weakest prediction. And by falsifying that scenario, one would falsify also the Dioschi-Penrose model in other limits in which one needs to look at the resolution of the mass density, which has the effect of enhancing the collapse effect. And we also discussed about the possibility to have parallel particles and measure the interaction between them, gravitational and so on. This was on the arXiv in 2016, but we were, in my opinion, a bit unfortunate with the review process. So it took quite a lot of time to be published. Good. So today I want to talk about some new idea building from these previous works, which is on this article that we have written with Talita Weiss, which was a postdoc in the group, Marc Rorayo-Ordez, who is a PhD student, Eric Torrontegui, who is a senior scientist in Madrid, expert on optimal control techniques, and Marcus Espelmayer, who most of you know. And the idea is to try to delocalize the nanoparticle over large scales using optimal control. And the idea is to use this for force sensing and also for entangling the motion of two particles via weak forces. But before I go into the details, let me motivate a bit more and give a perspective about what we want to do. And I always like to discuss this conceptual graph, where on the x-axis I qualitatively want to position this length scale of quantum delocalization in experiments, and on the y-axis the mass of these systems. And it's fair to say that there are these, in the context of generating superpositions of massive objects, there are these two well-established corners in this graph. On the lower right, there is the matter wave interferometry experiments, where small objects in the beginning, like single atoms, can be prepared on extremely large superpositions. There are these impressive matter wave interferometry experiments of single atoms where an atom is preparing a superposition of at the meter scale. Okay, so really impressive. On the other corner, there are the optomechanical experiments where interesting superposition states have already been prepared for mechanical modes associated to big masses, really, really big masses. However, all these states always have the length scale of the 0-point motion. So they are really tiny in scale. And that's why they are on this upper left corner of the plot. And somehow the goal would be to try to, the target, if you want, is to go to this upper right corner, which would correspond to not only large masses, but also large quantum delocalization distances. And why? Well, there are, if you want, two types of answers to this. One is, of course, fundamental. So having a large mass in a large quantum delocalization distance is fundamentally very interesting. First, because we would test quantum mechanics in a regime that it has not been explored, this area. Second, that's the regime precisely where most of these collapse models that have been discussed during the last 50, 60 years predict a breakdown of quantum mechanics. So by doing an experiment here, one would falsify all these collapse models that have been discussed and proposed during the last years. And also in the context of the interplay of quantum mechanics and gravity, if you want, entering into this regime would start to address the question of what is the gravitational field generated by a mass in a superposition state. If the mass is sufficiently large and it's very largely delocalized, there is the question of what is the gravitational field it generates. And for attacking this problem experimentally, one needs a large mass and a large delocalization. So traditionally, in the past, the way to attack, to go into that regime was as building from matter wave interferometry. And there are these seminal and beautiful experiments mainly done in the group of Macroscopic in Vienna, where they have been pushing the size of these atoms or of these particles that you can send essentially through a double slit to incredibly large scales. And if I'm not outdated, the record is by this impressive biomolecule that has a size of 10 to the 4 atomic mass units. So they send this basically through an interferometer and they see fringes. Okay, and this is and they are doing an amazing job, and they are pushing more and more. So I'm sure they would keep growing in mass in that from that direction. However, in the context of levitodynamics or of levitated particles, we believe there is an alternative approach to try to reach this area, which is by actually starting already from big masses that are cooled to the ground state and then try to delocalize the wave function to larger scales. And this is if you want, novel approach that some of us are pursuing, to start already with big objects that you can cool to the ground state and then try to delocalize them through large scales. And this is precisely the context of this talk. And I want to give emphasis on this change of scales. As I said before, the initial state, we need to start from a pure quantum state. And the way we know how to prepare pure states of massive objects is by cooling the center of mass motion to the ground state. And this has been achieved. And as I said before, the wave function in that case has a size of 10 to the minus 12 meters. To be precise, the standard deviation of the probability position distribution is given by the 0-point motion, that is 10 to the minus 12 meters. And now the goal would be, okay, can we somehow now delocalize the center of mass over scales much larger than the 0-point motion? And eventually, could one even get to delocalize a nanoparticle over length scales comparable or even larger than the size of the particle, which is for 100 nanometer particles? This corresponds to having to increase the wave function by 5 orders of magnitude, okay? Because this plot is not to scale. The wave function here is 5 orders of magnitude larger than that one. And this, how to increase the 5 orders of magnitude, is actually very challenging once you account for sources of decoherence, as we will discuss now. And I want to emphasize that even to delocalize, this is a less ambitious goal than preparing a quantum superposition state. Of course, this is a superposition state of waves, but it's a wave packet. And what I mean here by not a superposition, that this is a Gaussian state. This is not a state whose Wigner function is negative, such as the state you prepare after the double slit, where you have a wave packet on one position plus a wave packet on the other. This is just a wave packet that has been spread over large distances. So it's a Gaussian state, but it's of course pure. And if it's pure and it's delocalized over large distances, this, in our opinion, is also a very interesting state to prepare. Okay, and also not so challenging, not so I mean, also challenging to prepare. But this is an important emphasis because most of the proposals, also including the ones from our group, we always focus in the past on quantum superposition states, non-Gaussian states. Whereas in this talk today, I will only focus on Gaussian states that are delocalized over large distances. And we believe that here levitodynamics has three ingredients that are key to achieve that. The first one is that ground state cooling can be done. That's not unique to levitated particles, but it was a milestone that had to be demonstrated experimentally, and it was demonstrated now very recently. Ground state cooling of a levitated particle can be achieved experimentally. Second one is that we have the promise that these particles being isolated in high vacuum have the potential of having very high coherence. So to be very isolated to the environment so that they can prevent decoherence much better than other systems. But of course, this has to be demonstrated, especially experimentally. And the third one is that the potentials can be tuned. And this sounds like not a very impressive feature, but in practice is very useful. That the potentials can be tuned means that, for instance, the potential can be switched off, can be made shallower if you have an harmonic trap, can be even inverted, and so on. And of course, in standard nanomechanical systems that they are clamped, they have a fixed harmonic potential given by the clamping system, and in there you cannot modify it. So we will kind of exploit these three key ingredients. And actually, what we are proposing in this work is to perform what we call a loop protocol. Note that this diagram seems similar to the previous one, but it's not, because what we do is we start from the 0-point motion. We want to expand to a given length scale. And from now on, this parameter eta is going to be important. It tells me how much I expand the wave function compared to the 0-point motion. That's the factor eta. And we know that at that moment, the state is very fragile and sensitive. So what we want to do is, after we expand, we want to compress it back to the initial ground state. Okay, we want to expand and compress. This is like, if you want, breathing. Okay, we expand and compress. Why do we want to compress? It looks like this is including much more control and much more challenges to the experiment. But actually, first, there are three reasons. The first one is that this state, when it's expanded, is extremely fragile. So you want to expand it and close it. Okay, and therefore you want to compress it. First, if you compress it, it means you trap it again. So this is very useful for repeatability of experiments. So all these experiments in which you want to observe these quantum features, you need to repeat them under identical conditions. So you want a scheme in which you can repeat this experiment many times under identical conditions. And third, but not least, is that once you compress it, you can perform a measurement of its temperature, therefore of its purity, and hence you could check whether this process was coherent. In a sense, if you think deeply about the double slit experiment, the double slit experiment, we expand the wave function, and then we use the double slit just to measure that the state was coherent. So what the double slit does is prepare a superposition only because then after some time of flight, you see fringes in position, which is what we can measure. But if we were able to measure coherence in another simpler way, it would be beneficial. So here we just propose to measure this coherence by compressing back to the initial state and measuring what is the coherence. Of course, an experiment should repeat this many times, measure at the middle of the protocol and see that you have expanded, and then measure for other experimental runs at the end of the protocol and see that you are pure. And then in that way, it would not be a direct demonstration of a coherent protocol like the double slit is, but it would provide very strong indications that that was done coherently. So that was the goal. And how we want to achieve this goal is by making use of the dynamical control of harmonic potentials. And actually, you can phrase this problem into a rather standard optimal control problem. For instance, if you ask somebody, okay, imagine you have this potential, just an harmonic potential in which the spring constant can be modulated, including also negative values, the possibility of inverting the potential, and its upper and lower. So the strength of the spring constant is bounded by ω0. And I can modulate this as a function of time. And then I ask the optimal control problem of, hey, I start from this state, I want to expand it and compress it back. What is the modulation of this ω² that I have to consider in order to do this as fast as possible. Then actually it turns out that the time optimal solution is the so-called bang-bang protocol, in which you only use the extreme values of this spring constant, and you just change, you flip from positive to negative. So basically harmonic attractive and harmonic inverted. And I will go now through the protocol, but the idea is you start with a particle trap, then you do some shifts, inverted, harmonic, inverted, and this is the total amount of the protocol. It's going to be capital T, and then you go harmonic again, and you trap the particle. Okay, I will go to the protocol because it's very intuitive to understand why it works. So I will do that using this qualitative diagram of the Wigner function. So the initial state is assumed to be the motional ground state. Of course, you could consider also a thermal state with phonon number occupation close to 0 or below 1, but here just for the explanation, I consider pure ground state. So this is the Wigner function. So on the x-axis, I plot the position. On the y-axis, I plot the momentum. And the color code here is the Wigner function. And this white dot is just to know where the center is, okay, of the plot. So it's just for illustration purposes first. So at t equal to 0, we consider the ground state. So that's a nice Gaussian with some spread in position given by 0-point motion. Now, the protocol starts by inverting the potential and let the particle evolve in an inverted potential. And actually, if you have to think a few minutes to realize, but what happens in an inverted potential is that the particle, the Wigner function, actually gets squeezed along 45 degrees of freedom. And this is very different to free dynamics. If you would recall how free dynamics evolves, the spread in momentum should be constant, because in free dynamics, the momentum is a constant of motion, and it would just spread along x linearly in time. Here you spread along x and along p. And that's, if you think now from classical mechanics, that makes a lot of sense. The farther you are, the stronger the force is, so the particle accelerates. Okay, so that's why a particle that is more on the right has a higher velocity. So it's a very aggressive type of dynamics. And actually what happens is that the wave packet here expands in position exponentially in time. Okay, so it's a very fast growth of the harmonic of the wave function. And at the same time, you increase exponentially the size of the quadrature along 45 degrees. But if you would look now at the perpendicular direction, the variance also squeezes exponentially in time. So you are really squeezing along these 45 degrees. Okay, and for us that's good, because it means that we can expand the wave function really fast. Okay, we generate a squeeze state. Okay, now what needs to be done? So basically we have expanded the wave function. Now we want to compress it back. And to do that, what we do is first we let the particle now evolve in a normal harmonic potential for this particular amount of time to do the following. Note that the region of the waves that are on the right have a positive velocity. So that means they keep going to the right. So what we want is the waves that are on the right to have a negative velocity, and the waves that are on the left to have a positive velocity. So this can be achieved by a pi/2 rotation in harmonic potential, such that you rotate the Wigner function in this way. Now the waves that are on the left, they have a positive velocity, they want to move to the right. And the waves that are on the right, they have a velocity to the left. And now if you let it evolve by the inverted potential again, that sounds counterintuitive, you now let the particle evolve in the inverted potential, but actually the wave function refocuses. Okay, so in a sense, if you're very familiar with spin echo, that looks like a bit spin echo type of thing. But if you think also classically, it makes a lot of sense. You just, in a sense, you let the particle fall through the harmonic potential, then you put it on the other side, and therefore it goes up again. Okay, so after this time, these 3 steps, then we would put the harmonic potential, and if you have done everything perfect, you would remain in the ground state. So some features is to realize, well, as I said, that there is an exponential growth. Actually, that's a beautiful exercise in quantum physics, that if you would, it's very surprising if you want, if you multiply the product of 3 unitaries, one with an inverted potential, then an harmonic potential, and then an inverted potential. You multiply these three unitaries, and the part of the harmonic has this time, then the three unitaries are equal to the unitary in the middle. Okay, and this explains actually the loop. This shows that if you start from a state that is a ground state of the harmonic potential, after the loop, you remain in the same state. But if you look what happens at half of the time, of course, it's a very different state, okay, which is what you see in the plot. But this is actually very nice to realize this way. Okay, so that's the idea of this loop protocol. And for the rest of the talk, I want to discuss now two applications and then have a thorough discussion of decoherence. So the first, so that's the protocol. We expand, we compress, and now we want to look at applications.
Oriol,
the
if
first
I
application.
A question.
Yeah.
I really
Sure.
enjoyed your the previous discussion. So now, suppose if you have a small decoherence effect or some interaction, it would won't it destabilize the situation?
Yeah. I will discuss. This is what all comes now. It will come. Yeah. So as you have the right intuition, this protocol seems to be very sensitive to the external forces and so on. And actually, this is good. This is good and bad. And we will now analyze how good it is and how bad it is. But it's definitely, by definition, very sensitive. But that's what somehow we want. And in that context, the first application is to use the sensitivity to realize that, for instance, this protocol could be used to measure static forces. So imagine I now run my protocol in the presence of a static force. In a Hamiltonian, that's a term linear with x, with a small f that is a static. And I want to refer here, there was also a work by the group of Martin Plenio, where they also use these squeezed states for enhancing force sensing. So also, please go to this paper. And you see, if I run now the protocol in the presence of a static force, you see when I finish, of course, I'm displaced from the origin. Okay, I'm not back at the origin in phase space. So here, the Hamiltonian is positive. It means the force goes to the left. So that's why after the loop in phase space, I'm a bit here. So when I finish the loop and I switch on the trapping potential, now in phase space, my particle would rotate. And this is something I could use to measure the force. Very importantly, once you analyze how sensitive you are to this force, you can realize that in a sense, the force has been enhanced by eta, where eta is how much you expand. Okay, so you can make this protocol, it's eta times more sensitive to the external force than if you do it otherwise. And to be more precise with that statement, what we can do is, this is a bit, I will go through this plot, it is a bit full, but what one can do is, if you take the state after the loop, it depends on the external force. So you can calculate the quantum Fisher information of the state, and from using the Kramer-Rao bound, you can get a lower bound to the variance that any estimation protocol would give you for estimating force. Okay, and then you can plot what is the minimal force as a function of how long your protocol is, how long your loop is. And the longer it is, the more you expand. Okay, and here there are two lines. So first, on the x-axis, there is how long the loop is without units, t times omega 0. On the upper axis is giving you time in using omega of 100 kilohertz, just to have a reference. So that's a very fast protocol. In few microseconds, you can get that information. And on the y-axis, I write the force without units. And on the x-axis, on the right axis, I write the force in newtons for 100 nanometer silica sphere. And you see that the force starts to decrease exponentially fast. So the longer the loop is. And it's good to compare to the proposal and experiment done in the group of Lucas Novotny, where they just let the particle fall and let the particle evolve in free dynamics. They did that. They had a particle trap. They switch off the trap. They let it fall and they recapture it again. And they measured how far it was from the center. And in that way, they measured the force. So if you compare the scaling, of course, there is this enhancement by preparing this squeeze state. That's the first application. The second one, which I know is a hot topic in this colloquium, because you had these beautiful proposals of trying to entangle the motion of particles by a gravity. So here, what I could consider is very inspired by your ideas, is two particles trapped in two potentials. And note that I consider the configuration, the motion is parallel between the two particles, and they are separated by a distance d. Okay, and I assume there is a central type of force between the two particles, such as electrostatic force or Casimir or even gravity. Then you all know, I think, in this colloquium that, of course, you could now take this central force, and assuming the variance of the position in the well is smaller than the distance between the two harmonic potentials, you can do a Taylor expansion of the central potential, and then you get a correction to the frequencies of your harmonic potentials. That's why I put omega tilde, and also then a typical coupling of XX between the position of the two particles. And I write this coupling as a frequency G, and you see that has the right units because I divide by the 0-point motion. Okay, and as you can already guess, by enhancing the wave function, you would get an eta time from x1 and an eta factor from x2, so you have an eta square enhancing, an eta square enhancement of the coupling strength. Okay, so that means that in the presence of some interaction, by expanding the wave function, you have an eta square enhancement of the interaction. So what now I can plot is, assuming the two states are initially pure and the whole dynamics are unitary, I could then look at what is the purity of one of the states after the protocol. If there was no interaction, no entanglement between them, the single particle should be still pure. But now, because of the interaction and the entanglement you generate, if I look at the purity of one particle, this is a measure of entanglement. And that's what I show in this plot. In this plot, I show first the color means the purity. Blue means purity 1, hence not entangled. You have not entangled the motion. Orange means purity 0. That is, you have entangled the particles. And what I plot again is, on the x-axis, I plot the strength of the coupling, G, in units of the trapping frequency of the potential. And on the y-axis, I plot the expansion coefficient, how much I expand the wave function, eta. And just to have a reference, on the right axis, I say, how long does the protocol take? So as you see, this is extremely fast protocols. They take 10 periods of time, okay? And you would expand potentially to 10 to the 4th, 10 to the 5. And this is the strength of the coupling. And before I show you some examples, note that what this is telling you, if you concentrate at 10 to the minus 5, this means that with a coupling strength of 1 Hertz, if I'm able to expand 2 orders of magnitude, maybe 3, I would already entangle the motion in such a short time. Okay, so that's very important to be aware. And now, of course, we can compare what is this value for standard interesting forces. In particular, I plot here the coupling G in units of omega 0 as a function of particle separation, distance between center of mass positions in units of the radius. Okay, so, and first of all, when I say Coulomb here, I consider two particles, each of one having 1 Coulomb, so 1 charge only. Okay, and that's how the coupling is. You have for even separations of 100 times the radius, you would get couplings of 10 to the minus, this is careful, this is a very strong log scale, so this is 10 to the minus 6. Okay, so Coulomb with 1 charge, this would be between 10 to the minus 5, 10 to the minus 6. If you look at Casimir, this has a stronger decay, but you go down. And unfortunately, if you go to gravity, is of course a very low value of the coupling strength of the order of 10 to the minus 20, which in this plot would be even farther to the left, okay, much farther. So for this protocol, yeah, we will see now decoherence in a second, okay? So that's what the information of this protocol gives you. I hope this is clear, otherwise please ask me, because I will now move on to the discussion of decoherence. Okay, so what we all know is that macroscopic quantum physics is extremely fragile to decoherence. So far, I have discussed only unitary dynamics. And what we also believe is that this loop protocol, in this loop protocol, one can quantify this fragility very well, okay? Which would also make the protocol very sensitive to decoherence, which is bad, but also good if you want to understand your system before you want to go to these long-term goals. And that's the idea. So now we imagine you would do this experiment, you just expand, compress, and you measure the purity. And the question is it still pure or not? Okay. And of course, we know that most likely, if you push a lot, it will not be pure because you have suffered environmental decoherence. And this means for a levitated particle, many potential things: scattering of gas molecules, black body radiation, field fluctuations, coupling to other degrees of freedom, some of them maybe being unknown or exotic, if you think collapse models could enter here, and so on. So that's all what. So how do we analyze all these type of decoherence? Well, first of all, a very important source of decoherence is the scattering of gas molecules. And this is a very particular source of decoherence because air molecules have a very tiny de Broglie wavelength of the order of 0.1 nanometer at cryo temperatures. So, and as soon as you delocalize a bit larger than this scale, what really matters is that you don't scatter any air molecule, okay? Because as soon as you scatter a single gas molecule, the delocalization goes away. So you have to prevent a single gas molecule event. And if you calculate what is the time scale for that, this is given by this, a prefactor, then the gas, the typical mass of the gas, the temperature of the gas, the pressure, and the radius of the particle. And if you plot now this time scale as a function of pressure for a particle of 75 nanometers at the room temperature experiment, you get this plot, okay? Y-axis, this time in milliseconds, and x-axis pressure in millibars. So the ground state cooling experiments, they were in this regime of 10 to the minus 6, 10 to the minus 7 millibars, maybe 10 to the minus 9. There are current experiments where nanoparticles are already loaded at 10 to the minus 11 millibars. So in the short time scale, it looks like this is the window where experiments can operate in the quantum regime, from 10 to the minus 9 to 10 to the minus 11 millibars. For this size, that corresponds to a time scale of 1 millisecond to maybe 100 milliseconds. That means each experimental run should be faster than that time scale so that you don't scatter any air molecule. Note that this is for a small sphere, 75. This is an R square, so if you increase by 1 order of magnitude, you decrease by 2. So this goes 2 orders of magnitude below. So in our case, that was one of the motivation of this loop protocol, is that it's really fast. So for sure, each experimental run is faster than the time scale for an experimental run. For a scattering of a gas molecule. But for any proposal, one has to make sure that each run will be very fast. Otherwise, you scatter gas molecules. Then there is a very general type of noise that appears a lot in levitated dynamics, and we call it displacement noise. In a sense, this is like the center of the trap shaking, or anything that makes the center of the particle shake. And this can be modeled in the following way. So we are interested, so what we say is that now our Hamiltonian will have a contribution that is stochastic, that's a noise contribution that is due to a stochastic force. And this noise can be, and this stochastic term is a term that is linear in the position. Okay, so here I use convenient units such that I write x over the 0-point motion, I remove an h bar omega, and then I have this stochastic F1 variable, which is dimensionless. Okay, and this is just a force that in magnitude and sign is oscillating. Okay, this is a very general type of noise that we call it displacement. And if you would calculate all the quantum trajectories over this noise and then perform ensemble averages, you can derive a master equation for that noise. And this master equation has this dissipator, which is very important, which is of the type XX rho. And again, this has units of position. So I put a position square here, and then I have this gamma 1 that has units of frequency, and this is the decoherence rate, gamma 1. And gamma 1 can be very simply written as pi omega squared divided by 4 times the power spectral density of that dimensionless noise, which is defined like that. Okay, and this decoherence rate is evaluated at the power spectral density at omega 0, at the trapping frequency, where you can have resonances. Okay, and once you have that, then also just a connection, if you multiply this power spectral density by the 0-point motion, you have the scale of the vibrations of this displacement, okay, which you could then write in meters per square root of hertz. And just to give you a connection, for instance, the ratio of omega 0 over gamma 1, this is the number of coherent oscillations. That's what maybe in levitated dynamics that some people shouldn't, it would be very confusing if you call Q the Q factor, because that's the decoherence, the number of coherent oscillations, which is a bit different than the Q factor. So this tells you how many oscillations I could do in a trap by keeping the purity of the state. Okay, that's omega 0 over gamma 1. The phonon heating rate, if you cool down the particle in the ground state and then you let it evolve under the presence of this noise, the phonon heating rate will scale at 2 times gamma 1, as it is defined here. And now, very importantly, note that the decoherence rate actually scales with the delocalization, because this master equation has gamma 1 XX. So the real decoherence rate is gamma 1 times the variance of the wave function over the 0-point motion. That means the decoherence rate scales with eta square. Okay, when you are in the ground state is gamma 1, but as soon as you delocalize, this really scales with the delocalization distance, which is a manifestation of macroscopic quantum physics being very fragile to any noise, because now the decoherence is enhanced by eta square. And now what I can do is I can look at the protocol, repeat the protocol in the presence of this noise, and calculate what is the purity after the protocol as a function of gamma 1. And that's what this plot shows. I plot the purity of the particle after the loop. And again, blue means purity 1, which in that case is good. It means the process was coherent, and orange means bad, decoherence entered. And I plot it as a function of gamma 1 over omega 0. And again, on the y-axis, I have the expansion coefficient, and here the total time. And now I can review some standard sources of decoherence. For instance, if you were to do these experiments with a laser has an intensity that oscillates. And if the intensity, I apologize. So it has a power that it oscillates. And if the power oscillates, sorry, I don't say that correctly, I anticipated. So if you shine laser light into a particle, it suffers a scattering of photons, and this creates recoil heating. And the recoil heating is then proportional to the power of the laser. And if you put the typical numbers, this recoil heating is of the order of 10 to the minus 2 in this unit. So you are here. So that means that if you try to do this experiment with laser light, you will basically not able to expand basically much. And this we know. We know that in the presence of laser, you can perhaps do quantum stuff at the size of the 0-point motion, but if we want to expand, you should not use laser light. This we know, and that is shown by the fact that you are here. The second one is that any experiment will vibrate a bit. The center of the trap will vibrate a bit. And therefore, this gives me a gamma 1 that is proportional to the displacement noise, how much the center is shaking because of several reasons. And importantly, this gets a bit technical, but I think it's relevant, is that this displacement noise, since you have the 0-point motion here dividing, it's proportional to the mass. So this displacement noise is mass times larger than the displacement noise you have for a single atom. So, and that's very relevant. And for instance, if I look here, what is the displacement noise? In current experiments, I know they can achieve 10 to the minus 16 meters per square root of hertz. And maybe pushing better, you can go to 10 to the minus 18, so something like that. In any case, in the best case for the standard masses, you are at 10 to the minus 6, 10 to the minus 7. So you're around here. So this, in that case, center of trap vibrations would limit the loop protocol to 2 orders of magnitude, which is not bad. You could expand the wave function 2 orders of magnitude. The third one is, of course, also black body radiation. If the particle is hot, it emits photons, and by emitting photons, it suffers recoil. And this is also some type of displacement noise. And the heating rate depends on the temperature to a power of 6. And if I plot again gamma 1 as a function of bulk temperature, I get that in the best scenario that the particle is at room temperature, if it's optically manipulated, I have maybe 10 to the minus 7 around here. But if it heats up, like most likely in some of these optically cooling experiments, then you go to 10 to the minus 4, something like that. So, of course, if you would use a cryogenic particle, such as in the proposals of superconducting levitation and so on, you would get rid of that problem because you go down. Okay, good. That's in terms of displacement noise, but that's not all, because apart from displacement noise, you can have frequency noise, which is now a noise in which the trap frequency oscillates. And this can be modeled again as a stochastic force, but now this force, if you want, a stochastic frequency. So this is a noise term of that form. Now you have an x squared, so it's quadratic in position, but you see I write it with the same units as before. So again, that's a dimensionless stochastic variable that tells me how much the frequency oscillates. And now the associated master equation has a similar form. You don't have an x here, but you have an x squared. Okay. And just for the theories, this is a non-Gaussian dissipative term. So you have to be careful when you do calculations with it, because this leads to, in principle, non-Gaussian physics. And I still can define a gamma 2 here, a decoherence rate, which in that term, in that case, it's also proportional to omega squared. But now you have the power spectral density of that noise evaluated at 2 times the mechanical frequency. Okay. And importantly, now know that this decoherence rate even scales as a higher power to the expansion, now as at eta to a power of 4. So even if you think you have a very low frequency noise, if you expand a lot, this thing can dominate. And as you can imagine, you could also have a stochastic terms of higher powers, x to the 3, x to the 4, x to the 5, x to the 6, and all of them would be even more critically dependent on the size of the wave function. Okay. And that's what I want to say here. If you enhance a lot, at the end, frequency noise always dominates over displacement noise. Okay. And just to give you an example, if I now do the same exercise in the presence of frequency noise, then I get this plot, the same as before, but now on the x-axis, I have frequency noise in terms of gamma 2. And for instance, again, if you use laser light, the intensity of the laser light fluctuates, and this makes the trapping frequency of the optical tweezer fluctuate. And that means that the gamma 2 is proportional to the so-called RIN, the relative intensity noise. And for current good lasers, this value is of the order of minus 140 decibels, maybe minus 160 decibels. This means that this square root of S2 goes to 10 to the minus 7 hertz, 10 to the minus 7 of a square root of hertz. So if I now look at this plot, so and I have a trap frequency of 10 to the 5, and I look at 10 to the minus 7, I go to values of 10 to the minus 9 gamma 2 over omega 0, or maybe less, 10 to the 8. So you are here. So even with tweezers, you will not be able to expand to up to 2 orders of magnitude just because of the ring. But in the case of lasers, displacement noise, that is recall heating, is even worse. Okay. But of course, if you trap electrostatically, also electric fields fluctuate, and this might make your pole traps frequencies fluctuate, or magnetically the same, and so on. So this is not only applies to lasers, but any trap in which the field intensity fluctuates makes generates some frequency noise. And when you expand, this becomes very sensitive. Last but not least, in this protocol, you might thought like, hey, there is also error in the switching time. If I have to switch from harmonic to inverted to harmonic, how about I will not be able to do that exactly? So I will have some error in the switching time. Actually, if you now consider some error in the switching time, and you model this error epsilon as a Gaussian distribution with some width sigma, this is equivalent to frequency noise, because an error in time is the same as error in frequency. And actually, mathematically, if you consider that noise and you do the exercise, you realize that this leads to a frequency noise given by that formula. So it's proportional to the error in time square, sigma square. And for instance, if I assume I can change the potentials with an error of 1 nanosecond for these trap frequencies, this gives me a gamma 2 of 10 to the 8. So I'm also here, very little. So 10 to the 1, 10 to the 2. Okay. So I apologize for this rather technical discussion of decoherence, but I find it relevant in the context of discussing macroscopic quantum physics experiments. So the take-home messages is that the loop protocol, expanding maybe 2 orders of magnitude beyond the 0-point motion, might be within reach. That means creating a wave function that has of the order of 0.1 point nanometer. To go beyond that, at least with this idea of the loop protocol, requires it's a challenge, experimental challenge, and also think maybe about new ways to engineer this type of experiments. Of course, any macroscopic quantum physics proposal has to carefully analyze decoherence, because this is like a definition of macroscopic. The more macroscopic you are, the more sensitive you are to decoherence. This is almost 2 sides of the same coin. And actually here, because I know in this colloquium we are very interested about entangling by a gravity. In this loop protocol, this quantifies really well how challenging entangling by a gravity is, unfortunately, with this idea of that protocol. So one has to think about other ideas to be able to entangle by a gravity. And that's again, I show it, as I said before, you are limited maybe to expansions of 10 to the 2, 10 to the 3. So we are around here. And that means couplings of 10 to the -6. And these perhaps, which would be a very beautiful experiment, you could use that to entangle by a Coulomb, but to go to gravity, this is really another parameter regime. So that's what I wanted to tell you today. So just a quick summary. We have discussed this protocol in which we expand and compress. And this is a very fast protocol and extremely sensitive, which you might say it's bad if you want to push really hard the limits of quantum physics. But at the same time, it could also be a very interesting tool to do experiments in which you can then probe very sensitively your sources of noise. And I think for that context could be relevant. We have discussed quite a lot how the delocalization is challenged by the presence of decoherence. And we have shown that in principle, this could be used for force sensing and entangling by weak forces. Last but not least, I just want to say that we are trying to push this also experimentally with this generous grant, the synergy grant of macroscopic quantum superpositions, where the goal is precisely to prepare these superpositions of nanoparticles. And this is done in collaboration with experimental groups of Marcus Espermaya, Lucas Navoni, and Romain Kidan. And that's a project that starts basically now in May, and it should run for 6 years. With that, I would like to conclude by thanking the current team, and in particular, the PhD student Mark and Talita, who pushed forward this idea of the loop protocol. Thank you very much for your attention.
Great, that was really interesting. Thanks very much, Oriol. So let's open it up to questions. You can raise your hand, or you can type questions in the chat, and you're welcome to unmute yourselves and turn your video on to ask questions. We've got one already from Myungshik. Let's start with that.
Oriol, thank you very much for beautiful talk. I enjoyed it. I must say that I cannot. I mean, it's difficult to concentrate on the internet talk, but yours was great. Thank you.
Thank you. I appreciate
your switching time. So not only the switching difference, but also the on and off can take time, isn't it true? So that to change from one potential to another potential, it's not just instantaneous. Did you also consider the time to take?
Yeah, so this is of course important, and there are two aspects one should consider. First, when I say fast, it should be faster compared to the period of the particle. So it should be, you should be able to change faster than this 100 kilohertz kind of rate. What my colleagues say is that that should be okay. But also I want to make the comment in the discussion of decoherence. What is really important is not that you do it fast, but that you do it in a deterministic way. That's so that because if you don't do it very fast, but you always do it the same way, it would not be hard to reanalyze a bit the protocol and see what, just to calculate the dynamics in the presence of this finite switching, and then see what is the state you should get at the end, and maybe apply a bit of optimal control so that you go back to the ground state. So it's not critical that you do it fast, but that you do it without noise.
Okay. Yeah. And if you go, sorry, even though I said it was good, I liked it, still not very clear. So if you go to the slides, where you showed the graph for the Coulomb and Casimir and gravity. So you're saying that with your scheme, gravity is not easy, or
yeah, so this was a lot of information, and I had to go a bit fast. I mean, I have to be honest, we started thinking about that to try to maybe see if this could enhance the possibilities to entangle by a gravity motivated by your work. But at least in this analysis, this doesn't look good, which means that maybe that's not a good idea for entangling by extremely weak forces. And the reason is that you see, again, this plot, what it shows is assuming the dynamics are unitary, the color tells me what is the purity of one particle after the loop. So if it gets entangled, the purity should be 0. So it means orange. So you want to be on the orange area. And I do that as a function of the coupling strength G, which I write in units of omega 0. So you see, and then from that plot here, I can go and say, okay, look, if I'm able to expand to 4 orders of magnitude, I could entangle by interactions that are as weak as 10 to the minus 8. And then I can go here and I can look at 10 to the minus 8 and I see, oh, look, I could entangle by a Casimir if the particle is at 9 distances compared to the radius, or by a Coulomb even when they are super far. But gravity is still below. For gravity, I would need to go to the minus 20 regime in that scale, which is really, really far. Yeah, unfortunately, because the goal was the opposite, was to see that you could, yeah. Yeah, and then this is all only unitarily, but then you could still say, of course, you can expand maybe, you know, if you expand a lot, you can increase this by maybe 10 to the 10 orders of magnitude. But then, of course, as soon as you put a bit of displacement noise, so it's very hard to displace that much because all the noise scales a lot with that, unfortunately. But I'm not pessimistic. This probably means that, you know, probably we have to think harder to find other ways to do it. Yeah. So,
yeah.
Okay.
Right.
Yeah.
Andy, you want to ask your question?
Yes. Hi, Oriol. Fantastic talk.
Hi, Andy.
I had a question about your force sensing estimates. So in particular, I'm wondering what is the role of displacement noise in your force sensing,
yeah.
both for the processes that you talked about where you might have vibration or displacement, but also on the shot noise, just the detection of the final position of the experiment and the part for the detection.
We can maybe go, I didn't show this plot because it's too heavy, but I have it as a backup slide. So this is this is a bit heavy, but I'll just go for it. So these are all the colors are again the force sensitivity in the presence of displacement noise. Okay, so what you see in the loop, it basically bends and gets to a constant value. That just because it's displacement noise. If you add the frequency noise, it actually gets worse. Okay, there will be a minimum time where the sensitivity is maximum. Okay. Then if in frequency noise, it even gets worse if you make the protocol larger. So one needs to quantify. One should now look at the values we discussed before. For instance, in the presence of recoil heating, I said before there is a gamma 1 of 10 to the minus 2. So you would not gain anything in optical levitation. If you would do it in the dark and maybe go to 10 to the minus 6, you could improve versus free dynamics for the same amount of time. And with the advantage that you keep the particle in the trap, in a sense. So that's all the analysis we did, just to analyze the force sensitivity in the presence of frequency displacement noise. All the other aspects, which are of course very relevant in an actual experiment that lead to inaccuracies and so on, we have not analyzed.
I see. Okay, thank you. Yeah.
Can I pick up on that as well?
Yeah.
So what about sort of the shot-to-shot noise? So like you said, you have to average and
yeah, the shot-to-shot noise, do you mean that initially the particle would be on different positions? Yeah, but this translates into displacement noise. So you could, this is the same, because this is like having vibrations of the trap. So, but which is also relevant. So this, let me show you. Let me see. Sorry, 1 second. I just want to show this slide. Yeah. So this means that you should be at the level of 0-point motion. So you should make sure, you know, the experiment is repeatable such that you always start on a range comparable or even smaller than the 0-point motion. Otherwise, that's equivalent to having initial temperature, if you want. That would be equivalent to starting from a non-ground state, in a sense, because the thermal state also gives you some distribution of where it is in each experimental run. So that's always equivalent, which is of course also an additional challenge, that these things should be really well aligned. Or think about a setup where the alignment comes by construction.
Yeah. And do you tend to think that optical trapping is the best route, because it seems like you want a high trap frequency here?
Yeah, so that's I think the challenge we will all have, that in order to prepare pure states, it seems we need optical traps to get high trap frequency so that we can cool to the ground state. But if we want to go macroscopic, we don't want to do that with optical light. So as a natural consequence, probably a promising direction is to consider hybrid configurations.
Yeah.
Mm-hmm.
There's a question from Mark. Go ahead, Mark.
Yeah, again, this is just a beautiful talk, and thank you very much. I'm not by any means a theoretician, so I'm not going to claim to have understood a large fraction of what you presented, but it was beautiful. Nonetheless. And let me just ask, I mean, your sequence, your protocol, that is, of spreading out your wave function and then reconstituting it. Can you comment on that from the point of view of a Humpty Dumpty type of effect?
Oh, I'm not familiar with that effect. I apologize for my.
Well, that's it's Humpty Dumpty. There was this nursery rhyme where there was a fellow who was very fragile. He was an egg, actually, and he fell off the wall. And he broke into 1,000 pieces, and it was very difficult to reassemble him. And the idea is, of course, that one can take a wave function and split it, and then try to reconstitute it, as in time reversal, actually. And I'm wondering if that's the kind of thing that you've done with the.
Yeah, that's an interesting comment. Perhaps I might use this comment to emphasize something important, that the dynamics here are Gaussian, so are quadratic, so are very simple dynamics. So refocusing is kind of easy because you still have a very simple state. If you would try to refocus after you evolve in a nonlinear potential and you generate a nonlinear state, to refocus is much harder. So, and probably in this analogy you mentioned there are nonlinear physics involved, whereas here there are only linear physics involved, so refocusing is easy. But if I would do the same, I say, oh, I let the particle evolve in a quartic potential. And then I ask, what sequence of harmonic potentials should I do to refocus? That could even be impossible, maybe. So that's actually an interesting question. I don't know.
Perhaps we'll return to that. Thank you.
Yeah. I mean, you should reinvert with nonlinear dynamics. Yeah. Of course, you can always apply a UDAG and so on, but.
Yeah. So the next question was from Anis Rahman. He typed in the chat, how can we invert the potential in an optical trap?
How can we invert? Yeah, so for instance, in an optical trap, one possibility is to, for instance, if you take two tweezers and you overlap them a bit, you generate a double well. And therefore, a double well, in the middle of the double well, you have an inverted potential. That's one idea. The second one is you could also generate, you put two counter-propagating laser beams so that you generate a standing wave and then change the phase of one such that suddenly the particle is not at the maximum of intensity, but actually at the minimum of intensity by just changing the phase of one of the two lasers. So that would be two ways, for instance.
Yeah, sounds good. Anupam?
Yeah. So thanks, Oriol. So it was really very nice talk, and I really enjoyed your talk very much. So I think to point out one thing about this comment by Mark, I think he was making about Humpty Dumpty. So it's related to the coherence effect. So at the end of the day, if you have a very small amount of, if you can manage a very small amount of decoherence, then perhaps you would be able to construct your.
I apologize. Yeah, definitely. One, of course, if one accounts for all the degrees of freedom, then the evolution is unitary. So you always have the potential to make a U-Daga. And this is called, sometimes in quantum optics, we call it also quantum erasure. One could think about erasing this decoherence. But that would always mean to account for all the degrees of freedom. And for instance, in the case of laser cooling by active feedback, in a sense, they do that. They shine light, and the motion couples to the light, so it emits a lot of photons. But then basically what they do is they measure almost all the photons you scatter, and that's why they have so much information that they can then remove the thermal energy. That's a possibility. That's, of course, in terms of fighting decoherence, that might be a way to go, that you really control very well everything that is happening in the environment, so that you can post-select. This is also sometimes called post-selection.
So my next question is, I mean, so in optical traps, so to what extent, I mean, can we push the technology? I mean, idealistically, I mean, say, let's say, what are the requirements perhaps here to cool it as much as possible? Is that the biggest challenge?
I would say, I mean, cooling now, when you look at the impact of the purity of the initial state into these protocols, is not that big, to be honest. Once you start to be around 1 and a bit below 1, okay, yeah, you might need a bit larger time to see the fringes or so on. So the initial temperature is not that critical. It's more the noise that you introduce during the dynamics. And laser light, in that sense, is if you think about it, it's kind of a brute force approach. Now you just shine there a lot of photon just to, you know, to manipulate the particle. It's not you know, very delicate. So, for instance, you send light. No, this experiment should be in the dark. Should be everything without any photon. It should be really cold. And so, if we really want to push macroscopic, we should, I think, go in the dark, go in cryogenics, all magnetic, and that motivated this proposal we had on this chip with the superconducting, basically, because there we wanted to push everything very much. That's one route. The other route is also learning from standard quantum optics and quantum computation, is to go really fast, much faster than the time scales in which the coherence enters. And that's somehow what we are pursuing with that line. However, if you go fast, but you also expand, the coherence also goes very fast. So then it might be you don't win. So, and that's kind of the challenge. Yeah.
So it's a very interesting thought. So I think we are, because all these experiments are based on effects of QED. So, so if suppose, I mean, of course, it's just like a dreamer talking. Suppose if we could ever do the experiment with neutrinos, where the interactions are all weak interactions, which much weaker than photon, maybe some of these problems can be cured. But of course, handling neutrinos and doing this kind of experiment will take maybe another 100 years.
Yeah. Well, with neutrons, there were the matter wave interference with neutrons, right? Where they also, with bouncing neutrons from walls and measure gravity and so on. Yeah, definitely. But yeah, let's see.
And optical tweezers using neutrinos instead of light. That's ambitious. I like your thinking, Entan.
I raise this point because you see that in Fermilab they are doing these experiments, the Dune experiments. So they are actually creating quite a lot of neutrinos. But now, if I create some system where I only interact via neutrinos, because the interaction strength of weak interaction is much weaker than the photon, then perhaps I may be able to maintain the coherence of my system much more. But of course, I mean, it's much harder experiment to do. It's just a dream.
I remember once, I have to give credit to Florian Mark, where he told me, hey, maybe in intergalactic space, there are already beats delocalized over large distances. And we should try to measure them instead of making the experiments in the lab. Yeah.
No, very nice.
So Oriol, yeah, very, very nice talk, amazing talk, Oriol. So I had a few questions. I somehow cannot raise the hand here. So, anyway, let me ask. So what the main thing I'm curious about is, my feeling from working on the gravity side is kind of, you will need a non-Gaussian superposition eventually. So I'm just wondering whether when you have this very expanded, the diagonal squeeze state that you showed, right? Could that be like a starting point for like putting a slight different potential on one side of it?
But this is a very interesting point. I of course always thought about preparing superposition states, but actually I'm not so sure they are so crucial. At the end, how I see it now is that what the superposition states give you is a very simple way to measure that you have prepared a nice quantum state. That's in a sense what the double slit does. But would you say in the double slit experiment, is the state before touching the two slits more quantum than just after? I'm actually have my doubts about this. For me now, how I see is you prepare the macroscopic state already before touching the double slit. As soon as you touch the double slit, this is your probing. You start your process of probing that you have prepared a macroscopic quantum state. So, and we were always very obsessed, my group and myself, in preparing non-Gaussian states, superposition states. But I wonder whether that's a requirement we can you know, relax, because that makes everything much more complicated.
No, that I
you know, so
agree
that's
yeah,
and this has, it's kind of an obvious thought, but it only came quite recently that I realized about this somehow. So
right. So I agree with that partly, but of course also the support is much more on these two places. Once you, like when you're conditionally selecting on your double slit. Yeah, I agree that it's probably as quantum before as after, because you're finding the after by filtering, right? But the conditional state has kind of support in two places, right? Rather than, and this kind of, I think, helps in the maths in the way that you know, you can bring objects as close as their superposition distance. So it's like if you have to maintain Gaussianity, you have to work under the quadratic approximation, right? So
yeah, I mean, in my view, the superposition states give you a feature that can be measured that is clearly quantum, which are fringes. If you don't have the superposition, the quantum features are a bit more hidden, but they are there. And if we, for instance, technologically, we are very advanced in measuring these quantum features, maybe we should not invest so much on making this feature really evident, because that's not the problem. And whereas by trying to make these features evident, maybe we complicate too much the protocol and make it, and that was also, you know.
So maybe what you're saying is that in retrospect, you can find out those same features later on.
Yeah, of course it's harder like here, and it's not so direct. So you can, for instance, the problem is also we cannot do tomography of these states. So we can, it's not so easy to make tomography and measure the Wigner function. So what we know how to measure very well is the position. And that's why the double slit is useful, because it transfers the fringes that you have in momentum into position by the free evolution after double slit, and then you see them in position. If we were able to measure momentum, we would not even do the last part of the double slit. We would just pass through the, and we would measure momentum and see the fringes. But the only way we know how to measure momentum is by letting the particle evolve in free space. But if we have other measurements of quantum features, like what we propose somehow here, to compress and measure the purity. Yeah, I don't know, because since everything is hard enough, anything that we think we could simplify, I think it's a good direction, because it's already too complicated, I guess, for experimentalists like Andy. If we make it simpler, maybe it's better.
And can I ask you a little bit about your you know, your very first protocol of 2011, the optical x-square measurement?
Yeah.
Right? I mean, what is its status now? If you are thinking of really small, at least small superpositions, like you had quoted there, like 10 nanometers, 50 nanometers, would it still be kind of, is it still on the cards? Would it be still possible?
You see, but now, I mean, making this, also this proposal, just to how do we make a superposition? Oh, then we had to thought, okay, yeah, then let's make this x square measurement with a small cavity. It was complicating a lot, the experiment. Whereas now, if you would like to do it optically, I would just expand and compress. I mean, this would be a nice, at least, experiment where you show delocalization over scales larger than the 0-point motion, which it would be quite a milestone, because in optomechanical systems, that's very hard, because you are limited to the 0-point motion. They prepared now these fancy non-Gaussian states, which is really amazing, but it will be hard for them to delocalize the mechanical oscillator over scales larger than the 0-point motion, because you know, yeah, and then superpositions, of course, there are the ideas of coupling to the MBs, which is of course super promising, but for purely dielectric, you don't have nonlinearities. The only way is via nonlinear potentials or nonlinear couplings, but yeah, just requires time, I guess. I mean, and now there are many experimental groups, so they also, if you compare the last 10 years, I think the development now for the next 10 years will be much larger because there are many groups and they share a lot of developments and so on. So I think that, you know, there is a lot of communication between experimental groups. They share the progress, and it will be exciting times, I think.
Yeah, thanks very much. And maybe one last question regarding this your scalings of so from the sensing. So would you call it like a Heisenberg scaling that you have when you expand with time? Like is it 1 by root t or 1 by t?
To be honest, that's a good point. Let me show you again the plot. So I don't think there is anything genuinely quantum in this sensing scheme. So also, if you would like the free dynamics, it does. So if you look at the Fisher information, actually what you see, it has a scaling which goes with n bar, where n bar is the initial phonon number occupation. So what the scaling will be the same, it's just that it will go up, or so if you start from a thermal state, the same plot, you would have the same plot, but just at higher values. You know, like actually this experiment, it was completely classical, the experiment in Lucas Novotny. And if you would do it quantumly, this line would, I mean, this is already the quantum case. So in their case, actually, this goes a bit higher. This goes higher by. So see that we don't use any non-Gaussian physics, any, in that case, of course, if you prepare these non-Gaussian states, you have these tiny fringes in these tiny features in the phase space distribution that give you a lot of sensitivity. Here, in a sense, you could say we use a bit the squeezing, but we have not analyzed the scaling.
Right.
Yeah.
I mean, this probably points out to one general feature that squeeze. I mean, of course, many people do not regard squeeze states as genuinely quantum, but somehow what your work is telling is probably there as quantum as a superposition in some sense.
Yeah, right? I mean, it's a crazy state. If you look, I mean, I always, you know, if you look at this, I see again the simulation. I mean, because of course this is just for illustration purposes, but this is crazy. I mean, this line grows exponentially, but also if you look at the transverse quadrature, it also compresses exponentially. So it's really a highly, if you were able to expand such that this eta is 10 to the 4, this would be the largest squeezing ever of any harmonic oscillator, most likely. It's a crazy squeezing. If you would calculate this in decibels, would be a very, very large squeezing. And for instance, when they have an ensemble of spins, that is also an harmonic oscillator, they also do spin squeezing. And yeah, so this is a crazy state.
Just one comment about the squeezing. So squeezing you can also interpret depending on the occupation number, maybe. If it is a very large occupation number and you can get large squeezing, then the question will be that how to extract the quantum information. So
how
would we, I mean, like the comment which we are discussing now, that whether it's classical or quantum, and to what extent it is, I guess it will be, you need some tomography. I mean, what you were saying.
Yeah, so look, the problem is this doesn't rotate but if you would rotate a bit more, and this would be parallel to P, this means that if you would measure X, this would be localized to a length scale orders of magnitude smaller than the 0-point motion. You know, it would be like the center of mass would be localized to maybe a length scale of 10 to the minus 17 meters or minus 16. If you squeeze by 4 orders of magnitude, this means squeezing by 4 orders of magnitude means if you rotate and you go parallel to P, you measure position, and the position will be localized with a length scale of 10 to the minus 16 meters, which is smaller than the size of the nuclei. So, which is crazy. So, but of course, measuring this would be very hard by definition of being so squeezed.
Do you generate any like two-mode squeezing if this has both X and Y degree of freedom in this in your protocol, this kind of
yes, of course it was a one particle protocol. If the two particle protocols with interaction, so as you know well, for the interaction to create two-mode squeezing, you would need you could potentially if you would invert the two of them, I think, or if
more squeezing, because it's a time dependent. You are doing it in a time dependent potential, so there is some kind of time dependence here, I guess.
Yes. No, but if you would keep them at least in the harmonic, you have this beam splitter interaction, so you only have this entanglement that oscillates, not that growth. To generate the inverted, one should think whether if you keep one harmonic and the other inverted, something like that maybe, but I don't know. But no.
Yeah. Now I was more talking about two modes of the same, like two frequencies of the.
Sorry, I
same,
understand.
in the like more spherical inverted.
Yes, maybe. Yeah, that's a good idea. Maybe these are, one could look at these ideas with three-dimensional potentials and looking at X, Y, Z. Yeah, I thought you meant between two particles.
No. Yeah, of course that is the kind of there in the end of your paper that is there already. Yeah.
Yes, but.
Because that could be easy to measure, right? You measure X, Y somewhere, so the correlations maybe.
Yes. Yeah, and by the way, maybe now it comes to my mind, I should probably put more emphasis. I want to say it. So there is this nice proposal by James Millan, Ben Stickler on this rotor that it delocalizes and then it refocuses. So now I realize that one could also probably build some analogies and should acknowledge this proposal. And the advantage of their case is that since this is rotational degrees of freedom, the state is non-Gaussian. So it really generates a nice non-Gaussian state. And it also expands and compresses and refocuses in a sense. Yeah.
And at the end of your proposal, then how would you measure the purity at the end?
So in principle, that could be just do thermometry, like measure, like in normal cooling experiments, you could think about shining light and measure the width of the power spectral density. So this would be, since you have the same initial state in principle, you could just measure. So you could do two things. If you could measure the temperature, but also if it's displaced from phase space, it would rotate in the harmonic trap. So if you would measure the trajectory, you should see a bit of dynamics. Yeah, but I only thought about this, not more than that.
Great. Well, that's thanks for the discussion. Thanks for the talk.
Yeah, that's